In this video series, we are learning string-to-string library from Stanford NLP group. In the last video, we looked at how to compute the distance between different pieces of text. This text can be a single word or a paragraph. Okay. Today we are going to look at a similar thing. It's to measure the similarity between the two strings or pieces of text. In a way, the distance and similarity are related to each other. I mean, if the distance is more, the similarity will be less, and vice versa, right? So we can use these two metrics somewhat interchangeably. So as I mentioned, the library has a number of methods or algorithms to compute these four different things. Okay. Some of them are the old algorithms, some of them are recent developments. All right. Yeah, so we are going to do the string comparison to find out how similar the strings are to each other. Now, the way we define how similar they are, it can be a number of different ways. For example, we might be checking how many characters match, or we might be checking the longest common substring. Okay, we have, let's say, string 1 and string 2, and within this string 1 we might have some substring which exactly matches with string 2. So we look for the longest common one, and this subsequence comparison and also this structural alignment. We'll see examples of all these. Okay, so there are different algorithms to compute the similarities. The most famous one, probably used, I guess, 90% of the time, is this cosine similarity. And it's also being used a lot in vector embeddings or the vector embeddings similarities, right? To extract similar images, semantic search engines, etc. So I have a course on vector databases. Please check out that playlist where we use cosine similarity to build a number of search engine, semantic search, image retrieval, facial similarity search, etc. applications. Okay. Just install this library using pip if you haven't already. Now the cosine similarity, it's easy to compute. Basically, we have two vectors x1 and x2. We compute the angle between the vectors, and that will give us the cosine similarity. So the smaller the angle, the more similar the vectors to each other. Okay. All right. Very simple, from string to string. Today we are looking at similarity and explore, import the algorithm cosine similarity and instantiate. And these are two toy examples. So basically here we have a torch tensor and another torch tensor. We can supply these torch tensors also to compute the cosine similarity, or we can also supply these numpy arrays. Okay, because these two are the same, we'll get the same answer. Right, this is just showing this library can work with the torch tensors as well as numpy arrays. But let's come to the actual text. Okay. All right, now in order to do the string similarity, we need to first create these embeddings. I hope you already have some familiarity with embeddings. So basically, given any form of data, it can be text or words or images or audio files, etc. Using some pre-trained ML models will represent the data in some higher dimensional mathematical in the form of vectors. Okay, for example, let's say we have these four words: cat, dog, phone, computer. Now these don't have to be words. This can be piece of text. I mean, it can be a paragraph, document, anything, right? So we use these pre-trained models to convert these data elements into vectors. Now, irrespective of the size of the string, all vectors will have same dimension depending on which model we use to create the embeddings or compute the embeddings. And then once we create the vectors, we can compute the cosine similarity, right? Because we can compute the similarity only between the vectors. So here we are importing this GLOW embeddings, which is one of the NLP models. So as a this library, it has support for GLOW, FastText, BERT, as well as many number of other recent as well as traditional large language models. So you can import any one of the models and then compute the embeddings. Okay, so these are the 4 words, and here we are computing the embeddings for all these 4 words. Okay, actually let's look at the embeddings for one of it. What we will do is, so here we have embeddings. So as you can see, this is 4 tensors. Okay, and if you look at the first one, can I print like this? Yeah. So this is a tensor or the vector. I think I can compute length, not like this. Maybe I can do shape. Yeah. So it has a size of 50. Okay. So what this means is we have converted the word cat into a point in 50-dimensional space. Okay. And similarly, we have converted dag into another vector of size 50. Now, because these embeddings are computed using the language models, they can understand what each piece of text represents. So what happens is the data elements which are similar to each other will have the vectors which sit closer to each other in space. Now just imagine instead of this being a 50-dimensional vector, let's say this is simply a 2-dimension vector. So let's say this is converted into 2 points, x and y. So imagine we have this x and y coordinate system. So this point we can represent this this one, which is the cat, we can represent as a point in this 2-dimensional space. And similarly, we do the we compute the embeddings for dog. That will be another 2 points. Okay, that also we can represent as a point. Now we compute these 4 points and we'll have those 4 points in the 2-dimensional space, right? And then we can compute the cosine angle between each pair of these 4 vectors, right? And these vectors, if the words or the text they're representing is similar to each other, then those vectors also sit closer to each other. Okay, so that's how the embeddings work. All right, so we have 4 embeddings. We have computed 4 embeddings, and then we are going to compute the similarity matrix. So basically, we are going to build a 4x4 matrix where we compute the similarity of each word against the remaining 3 words. We are also going to do this against the same word so that we have this 4x4 matrix. I'll show that matrix in a minute. So here we just initialized a 4x4 matrix with all zeros. And then here what we are doing is, with these 4 vectors, we are going over the vectors one by one, and then the inner loop, it also loop over these 4 vectors. So for each vector from here and for each vector from here, we are actually computing the cosine similarity. Okay, so for these each pair of vectors, we are computing the cosine similarity and storing in this variable result. Now in this matrix, we are simply updating those elements using the indices I and j. Okay, and while doing this, we are also printing the cosine similarity. Now from this, we know dog is more similar to cat, vice versa, and also phone is more similar to computer, and dog is far from phone, far from or different from computer, right? So the cosine similarity between these 2 vectors or words should be smaller, between these 2 should be smaller, and for all the remaining pairs, it should be larger. So let's see if that's what's happening. So the cosine similarity between the glove embeddings. Now, if we use a different embeddings, this value we get will be different, but we still have this separation, right? This value will still be high. It may not be 0.92, but it will be still closer to 1. and the value between cat and phone, which are not similar, it will be low. Okay, so as you can see, between cat and dog 0.92, this should be low, this should be low. So between cat and phone, cat and computer should be low. Similarly, dog and phone, dog and computer should also be low. And finally, between phone and computer, it is high. As you can see, between cat and dog, it is more higher than phone and computer, because these two represents these animals which always go as pet animals, go together. Whereas these ones, even though both are electronics, those are not exactly the same. Maybe an iPad will be more closer to these than phone or computer to each other. Okay. All right. Then just the same results we are going to see in a couple of different formats for better understanding. Okay. The library also has some convenient utility functions. For example, plotting the heat map. Okay. So all we are doing is we are simply inputting the similarity matrix, which we have computed here, which is a 4x4 matrix because we have 4 words. And then just giving some title, what should be on x-axis, y-axis, the labels, etc. Right? So the labels here, as you can see along the diagonal, it will be 1 because we are computing the similarity of the word against itself. So cat versus cat, dog versus dog. Okay, that makes sense. Now cat versus dog. Also, as you know, these metrics are symmetric between cat and dog, dog and cat will be the same, right? So it's just look the lower left half. So between cat and dog 0.92, here we have the high value, and similarly here we have the high values between computer and phone. This region we have the low values because they are not similar to each other. All right, and then what we do is, so here we computed for simple words. We can do the same for piece of text or the paragraphs, right? So here we have some text. This is talking about some favorite drink in the morning, some beverages. It is talking about some beverages. Whereas the second one, it's talking about this Richard Feynman, who is a physicist, his contribution to the science electrodynamics. And fourth one, coffee, again beverages. So the coffee is one of the most celebrated beverages, blah, 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 blah. So as we can see, 1 and 3 are more closer. And the fourth one, it's again related to, physicist, another physicist, Albert Einstein. Okay. All right, about general relativity. So 1 and 3 are closer to each other. 2 and 4 are closer to each other. Now it's exactly the same process. So this time we will be computing the embeddings using the paragraphs of text instead of simple words. Okay. So we are doing the same. We computed the embeddings for these 4. It might take a while because here we are using this BERT large language model from Facebook. So the model first gets downloaded. Now, if you have slow internet connections with slow RAM, run these notebooks on Google Colab. I have a good system, so I ran it locally. But on Google Colab, it has a much faster connection to these large language models. So downloading even this 971 MB, it probably takes maybe 10, 15 or less than a minute. Okay. All right. So here, notice that here we are using a different model, Facebook BERT model, whereas here we used these glow embeddings. All right. Okay. We have computed the embeddings. What are we doing? It's just, we are printing the same stuff. We are just saying, okay, sentence 1 is this, 2 is this, 3 and 4 are this. Exactly the same thing. We have initialized a 4x4 matrix. All elements are set to 0, and we are creating these 2 loops so that we can compare each piece of text against the other piece of text. Okay. Doing pretty much the same. So between sentence 1 and 2, it's low, whereas between sentence 1 and 3, it's high, which is about tea and coffee. Similarly, 2 and 4 are about physicist. So 2 and 4, we have the high values, and for the remaining, we have the low similarity. All right. The same thing, we are plotting this heat map are the similar to confusion matrix. So here we have the sentences 1, 2, 3, and 4, and doing the same thing again. A sentence 3 and 1 are closer to each other, 4 and 2 are closer to each other. All right. So this is pretty much similar, but we have so here we have changed the model which is used to create the embeddings, but we still computed the cosine similarity. Similar to cosine similarity, we have a bunch of other metrics, right? So these are actually coming from large language models used for embeddings and natural language understanding, but they also have some similarity metrics which we can make use of. Okay, so let's look at this BERT and BART. Where are we here? BERT. Yeah. Now, what these models internally doing is not that important for the for our purpose of learning this library. But if you are interested, you can go to Hugging Face. Hugging Face has excellent documentation about most of the LLMs. So here you can read which data is used to train the model. I mean, some internal details of the algorithms, what metrics are used for model evaluations, etc. So if you are interested, you can head to Hugging Face and simply search for this BERT based unseized. It will take you to Hugging Face, and this is the second model BART. So you can do the same. I mean, you can read more here. All right. Pretty much the same from Similarity. We can import BERT and BART modules, initialize them. Okay. Again, this will take some time. For example, this one, second model is 1.5 GB, so it will take some time. Now we have 4 sentences. Here, earlier what we did is, we did this 2 for loops, right? We compared one against other using these indices I and j. Whereas here we are doing it slightly differently for efficiency. Once again, where are we? Yeah. Okay. So we have 4 sentences, right? S1, S2, S3, S4. So we are just preparing the source sentence and target sentence in this format. So we are just creating these pairs, so which will be 16, right? S1 against S1, S1, S2, S1, S3, S1, S4, and then S2, S1, S2, 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 S3, and so on and so forth, right? So we are just making these 16 pairs so that we can supply all these 16 pairs at the same time rather than looping over each pair. Okay. So again, when preparing these pairs, we are still using this for loop, but once we create these pairs of sentences, we can just input them rather than calling the model in the loop, which is what we did earlier. Okay. So we created these 16 pairs of sentences, and similarly, just pass the source and target sentence to the compute module of this BERTScore. Okay. All right. So this will return 16 values, right? Because we have 16 pairs of sentence, and we are simply reshaping the list into a 4x4 matrix, which is what we have here. All right. We can do the same heat map. Okay. It's the same stuff. Let's move fast. BARTScore, pretty much the same, source and target sentence, and again convert the list to 4x4 matrix, and here we have the scores and then the matrix. Okay. So all right, and finally we are going to look at this Jaro similarity. The Wikipedia has more simpler explanation of this mathematical formula. So basically it's looking at the first text length, second text length, how many matches, how many mismatch, and this transposition, which we saw in an earlier video, where we can swap the characters, right? So it's doing those sorts of computations to compute this, what is known as Jaro similarity. Very much the same, just instantiate and supply 2 pieces of text. And here the score is 0.88. So it's a normalized score between 0 to 1. It is form bill A, and it's somewhat similar sounding with most characters are the same. So it has high similarity. And more realistic scenario, here we have a document which is this, I guess this is Shakespeare's what is called omelette tea or something. So here we have the first in one format, I guess, to be or not to be, etc., etc. And then here we have a second version, I guess a slightly different version. Okay. And when we have these pieces of paragraphs of text, we can obviously do the tokenization. So we are going to compute the similarity at the character level, also at the word or tokens level. So in order to do at token levels, we are using this tokenizer, and we are going to create tokens based on this space. Okay, here we might have a new line or a tab. Maybe, for example, this text is separated by tab instead of a single space. Here we will use the tab, right? So we are essentially informing the tokenizer how it should create the tokenizers out of this text. All right. So for the first one, for the second one, we have created the tokens and we are computing the Jaro similarity. And by default, so here we are supplying the tokens, so it will compute the similarity at the word level. Now, if you supply the text as it is, it will do the same at the character level. Okay, so here we have the scores between the word level 0.66 and between the character level. So this one is at the word level, which is using the tokens, and this one is at the character level. All right, that's it for video. We can use different algorithm. Maybe some algorithms give better similarity scores for our application, but in most cases we use this cosine similarity. But the library is so standardized that importing and using any algorithms is exactly similar. Okay, that's all for this video. Thank you very much.